Hi everyone, in this presentation we are going to see that what are the benchmarks that are extensively used in the research work for the floor planning, placement and partitioning in the VLSI design system. It lies in the physical design cycle of the VLSI design cycle. Now we are not going to discuss this thing in detail in this presentation. Now you can see that the partitioning, floor planning and placement, this lies in the physical design step of the VLSI design cycle. Now, what are these MCNC benchmarks? The MCNC stands for Microelectronics Center of North Carolina. Many floor planning and placement papers refers to MCNC benchmark netlist. The benchmark files are in YAL format. YAL means yet another language format. Now, what is this YAL? The YAL language was developed by Brian Priest and Ken Roberts at Xerox PARC in 1987. YAL is used to represent the current MCNC benchmark netlist circuits. Now the current is not the type of current that we used to represent in amperes, but it's saying that previously we used to represent the netlist circuit in some another way. Uppercase describes the keywords of the YAL language. All the words that are described in uppercase are the keywords for the YAL language. Now this is the syntax for the YAL language. Here we define the module. This is the keyword for the YAL since it is represented in the uppercase letters. In the angular brackets we give the module name, and the next is type, again in the uppercase letters, so this is the keyword for it. In the angular brackets we give the type of the module, that can be journal, pad, parent, etc. And in the next statement we describe the dimensions. In the dimensions, again in the uppercase letter, that means it's the keyword for the YAL language, and then we give the x and y dimensions for that particular module. And in this case the origin is described in the last, and we used to represent this thing without any commas in the counterclockwise direction. We will see this thing in the example later on. And then the IO list, we describe the IO list for the particular module for that thing, and what is the syntax for it. Again in the angular brackets we give the signal name, that means the signal that is coming out from that particular module, and then we give the terminal type, that can be your input, output, bidirectional, etc. In the square brackets we describe the optional items, means the optional things that we can represent in the IO list particulars. So later on, after describing the IO list, we end this thing list by giving the keyword and IO list. And if we are going to represent some parent module that combines some modules within it, then we describe this thing by network, that how the various submodules are connected with each other within that particular parent module. And again we end that network by using the keyword and network. Lastly we describe, we just write down the end module to end the module. Now what are modules? A module is a definition of a circuit being layout or a constrained primitive cell. Each module has a list of inputs and outputs. Each module has a unique module name and a module type. The module types can be standard, pad, journal or parent. Now what is the standard type of module? It's a module that is placed according to the row layout style, that is a standard cell. Okay, let us take an example. When we are having a bigger module, and in this the submodules are there, if the submodules are having the similar characteristics, that means the standard type of module that is repeated again and again, and these are connected in the row layout style, then this type of module is known as the standard type of module. The next one is a pad. A pad type of module is having the inputs and outputs only. Next one is journal, a leaf module that is placed according to the journal layout style, that is a macro cell. When we are having the submodules which are having the dissimilar characteristics and these are connected to each other through nets, then we can say that it's a journal type of module. Any module that is having a particular characteristics is known as a journal type of module. The last one is a parent module. Now the difference between the parent module and the above three types of module is that a parent module is a soft type of module, while the above three modules are hard type of modules. Now what is the difference between these two? A module is classified as hard if its characteristics, that is dimensions and terminal locations, are defined. A module with undefined characteristics is soft. Means a soft type of module is a flexible one. That means its dimensions and terminal locations can be changed. Now let us take some example for it for this. When we are having a parent cell or a bigger module in which the submodules are interconnected to each other, the submodules are having a defined characteristics. That means the dimensions and terminal locations are defined, while we can change the location of these submodules within that parent module. When we change the locations according to, so that the functionality of that module or the chip can be optimized, that the outer terminal locations or the dimensions will have different dimensions or terminal locations. So the next one is IO list. Each module has an IO list which describes the external net connections of the module. For each connection, the signal name identifies the net. Each net has a unique signal name. The two nets cannot have the same name, otherwise the language will not understand that which signal we are referring to. The terminal widths are described in microns. That means almost all the dimensions are defined in micrometers in the YAL language. The terminal type can be one of the following. The first one is I. I means the connection is input to the module, while O means that the connection is an output from the module, while B means that the connection is bidirectional. That means a connection can act as input or output. While PI is the paired terminal input, PO is the paired terminal output, and while PB is a bidirectional paired terminal. Now the difference between the IOB and PI, PO, PB is that when we talk about the submodules, then it is having the terminal types as IOB, since these are not going to communicate with the outer world, while PI, PO and PB, these are the terminals for the outer module, the bigger one module that is going to communicate with the outer world. So the terminal type for the parent module will be written as PI, PO and PB. The next one is F. F is a feed through signal. Now this signal is not used by the module, but the connection is used to pass the signal through the module. Sometimes it happens that to optimize the functionality of that chip, we need to pass a particular signal through a module. So this type of signal is known as feed through signal. The next one are PWR and GND. Now these type of terminals defines the current and voltage characteristics of that particular terminal. Now we can say that we can define the PWR and GND as the power connection as well as the ground connection. Now let us try to understand the YAL language through an example. I have taken the example from the AMI33 benchmark. Now this AMI33 benchmark are having 33 modules within it. So I have taken a BK1 module out of these 33 modules from the AMI33 benchmark. Now for the convenience I have written the syntax for that module also here. Now you can compare these two. The first one is module in the capital letters. The next one, the module name is defined here, and the module name is BK1 here. Now the type of this type of module is journal. The next dimensions are defined. Dimensions are again in the uppercase letters. Now the dimensions are written in x1, y1, x2, y2 and so on up to xn, yn. Now these dimensions are written in the counterclockwise direction, and again these dimensions are in microns. Now let us try to compare these dimensions with this figure. The first dimension is x1, y1, and also no commas are written within it. So 336 and 0, this is x dimension and this is the yth dimension. So this is here 336 comma 0. The next is x2, y2, so this is 336 and 133. It is here. The next one is 0 and 133. That means the x direction is 0 while the y direction is 133 micrometers. So the dimension is here the last one is the origin, that is 0 0. You can see that the dimensions are defined in counterclockwise direction, that means it is like this. And also we can find out easily that what are the lengths and breadths of this module, and what should be the area for this module. The length and breadth of this module is 336 micrometers by 133 micrometers, and the area consumed by this module is 336 micrometers cross 133 micrometers. Okay, next is the IO list. That IO list is defined here in the uppercase letters. So after this semicolon we define the signal name. The signal name for this, the terminal is P underscore 0, and the terminal type is PWR. Next we define the location of this terminal, and it is 175 0. So where this terminal is going to be, since the y direction is 0, so it should lie somewhere here. That means P underscore 0 should lie somewhere here. And yes, what is this the layer? Okay, the next one is the width. Okay, width is 1 micrometer is the width for this terminal. The next is layer. What type of layer that we are going to use within it? The type of layer can be metal 1, metal 2, it can be poly, etc., like P diffusion, N diffusion, etc. So the type of layer that we are using here is the metal 2. Generally the outer connections are written are having the metal type of layers. So the next one we define the current and voltage characteristics. That means it can withstand 0.003 amperes of current, that means 3 milliampere currents, and the voltage it can withstand is 2 volts. The next one is same one, like P underscore 1 PWR 105. Now these we can write down here GND also, since the PWR and GND are used to define the current and voltage capabilities. It can be 0, it can be 2 also. So again, since if we are having a VDD connection, the ground connection is again going to withstand the 2 and that particular type of current that is going to generate from the source. So the P underscore 1 is having the dimensions again 10520. That means the y direction, the y-th axis location is 0, so it should lie somewhere here. And again the terminal width is 1 microns, and it is having the metal 2 type of layer. The current and voltage are defined. So again we define the list of terminals for this BK1 module. So how many terminals are there for this module? It is starting from P underscore 0 so on up to P underscore 12. So these are having 13 terminals. And let us take another example. Let us take this example, like P underscore 10. Now it is of type bidirectional. That means it can act as input as well as output. And what are the dimensions for it? X dimension is 112, while the y-th dimension is 133. 133 dimension is here. Okay, and the x dimension is 112. That means P underscore 10 connections should lie somewhat here. Lastly, we end the IO list by using the keyword AND IO list, and we end the definition for this BK1 module using the keyword AND module. The network example from AMI 33 has been taken here. Now this network is for the parent cell, and it defines the various submodules that are connected to each other through the various signals. I have taken the syntax for the convenience. The syntax for this was network instance name, means for every module we give the instance name and then we define the various signal names. Now these signal names you can compare it here. After writing the network, the instance name for this module is C underscore 0. The module name is BK9D, and then we define the various signals for that, like GND, P2G, P2F, P1G, P1F, 399 and so on. These are the signal names, that how the various signals are connected to each other. And again for the 33 modules in AMI 33 benchmarks, the way 33 instance names, the different instance names are given and the various signals are given. And we can see that let us take this example, C underscore 1. This is P2G signal and this is P2G signal. That means this is the first, second. This is the second terminal and this is 1, 2, 3, 4. This is the fourth terminal for BK9C. The second terminal for BK9D and the fourth terminal for BK9C are connected to each other. Also, this fourth terminal and the fifth terminal are connected to each other for this BK9C. And so on. We have taken the example for BK1. Now one thing is to remember that the number of signals that should be same as the number of terminals that we define in the modules. Like for the BK1 module we are having 13 terminals, and for the BK1 module again we define the 13 terminals. The GND power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And also the first signal name that is defined here, it corresponds to the first terminal name in the module. That means GND is having the characteristics of P underscore 0. The next one is power. That means P underscore 1 is connected to the VDD signal. The next terminal corresponds to the P2G corresponds to the P underscore 2 here, and so on up to lastly 311 signal name is having characteristics of P underscore 12. So this is how the various modules are connected to each other through various signal names. So let us try to understand the ME33 benchmark circuit through its coding. So we define the various modules as we have learned before, that we give the module name and type, dimensions and IO list. So these are the terminal names for the BK1 module, and we can count the number of terminals for it. It is starting from 0 to 12, so it is having 13 terminals, or we can say that module BK1 do have 13 pins, and we define 33 modules like this. Okay, this is type journal. Okay, lastly we define the final module for it, and we give the type as parent, and the module name for it is bound here. So we give the dimensions and IO list. We can count down the final output, the final parent pad terminals for it. So we can count down the number of terminals for the parent module. ME33 parent module do have 42 input outputs or terminals for it, and we can see that the difference between the previous submodules and this final module is that first it was bidirectional, now it is PB. That means it is paired bidirectional now. There are two terminal types are of power, and yes, all of them are of type paired bidirectional. After defining the parent module, we define the network for this, that how the various submodules are connected to each other. We give the instance name and then module name, and according to the symmetry here, that how this BK90 has been the terminals have been defined, we define the various signals for it. So the network should have 33 instance name for it. That's it. Some of the list of the MCNC benchmark are as follows. We have different benchmarks for the MCNC: APTE, Xerox, HP, AMI 33, AMI 49, and we do have the various specifications for it. Like the number of modules for APTE is 9, for Xerox 10, for HP 11, for AMI 33 it's 33 modules, AMI 49 modules. We are taking the example of AMI 33 till now. Now what are the number of IO pads for it? The number of IO pads is equal to the number of pins or terminals that the parent module do have. In AMI 33 we have seen that the parent module has 42 number of terminals. That means it do have 42 number of pins also. And how many number of pins are there? So to find out the number of pins, we have to sum up all the pins of submodules as well as for the parent module. Now the parent module for AMI 33 do have 42 pins. To find out the number of pins, we have to add up all the number of pins of various submodules. So what I have done is that I have just write down all the number of signals for the AMI 33, and after counting we have found out that the number of words or the number of pins to be 480. That means the number of pins for all the submodules of AMI 33 benchmark are 480 pins. So 480 plus 42, how many number of pins are there? It is 522 pins. To find out the number of nets, the number of nets is equal to the number of internal connections of the various submodules that has not been repeated. Like for the ground, it may have been connected to various submodules, but ground net is considered to be as one particular net. So to find out the number of nets, we have to just remove all the number of redundant signal names of the various submodules. To find out this thing, what I have done, I have removed all the number of this redundant pins or the redundant signals. So what I find out, it has, so the number of nets have been found out to be 123 for AMI 33. So this is the number of nets are 123. One thing is more that when we talk about this thing, it do have P21, P20, P19. It may be coming from some type of module, like we can see it here. Like let us find out that where is P23. Let us take the example of this P23. This is the terminal of the bound module, that is parent type of module. So this is P23. Let us find out. It is P23. Find next. Now this type of terminal will appear once only in the network, since it is going towards the outside of a particular submodule. Let us type again. It will come in the parent module only, but in the network it will come only once. Yes, it will come on only once here. So we can say that BK7 is producing the pad terminal output, whose instance name has been given to be C_6. So this is all about the benchmarks. I hope that this presentation is going to be useful for the researchers who are doing their research in the field of VLSI design, particularly in floor planning and placement. Since these benchmarks are standard, these are certainly going to be used in your research work. For any other questions or queries, you can mail me at brainiacsolution7@gmail.com. And thank you for the listening.